For the third session of this lecture series. I'm Professor Sachin Panhalkar as a coordinator for the Center for Climate Change and Sustainability Studies. I once again welcome all of you. In the last two lectures, what we had, that is of the Anil Kulkarni sir as well as Vadnere sir, they have emphasized the importance of the flood modeling, real time, how we can assess. And regarding to that, today we have planned this session. First of all, I would like to welcome Professor R.K. Kamath sir for chairing this session, who is in charge Dean of Science and Technology Faculty, as well as Director of DOT, as well as he is also working as Professor in Electronics Department. I would like to also welcome our eminent speaker, Professor Venkatesh Merwade sir, who is with us, who is working as a professor in Pardue University, USA. Welcome, sir. And I would also like to welcome all the dignitaries. Nandakumar Vadnere sir is also present here. Pradeep Purandare sir, PD Raut sir. They are also participating in this event. So welcome all of you for this third session, and which is a very important one regarding to the flood management as well as the modeling, what we were discussing. When we are talking about the water, it is basically called elixir of life. And if we have the water in the desert area, it creates basically heaven over there. But at the same time, we are also facing the problems from the water, various kinds of disasters like the landslides, as well as flood are also being created by the water. So today's topic, I would like to say, who is very familiar with the nature. That is Professor Venkatesh Merwade we are having with us. When this water interacts with the lithosphere, when this water falls on the earth's surface, then how much of the part of this water will percolate, how much will contribute into runoff, what kind of losses we may have, who can assess, who has explored all those things regarding to by using remote sensing, GIS, as well as nowadays we are talking about the IoT or the data mining, or when the water flows through the rivers, what kind of impact we may have. So for that sake, who can explain this phenomena in a much more scientific way, and how we can control the flood. When we are talking about the disaster management, then mitigation, preparedness, response, recovery, these four phases are much more important. But very little bit emphasis which is being given on the mitigation phase. And in that, I think the flood management or the real-time flood monitoring plays a very crucial role. So I welcome Professor Venkatesh Merwade sir, that you have accepted our invitation and you are here with all of us. Thank you, sir. So this is my duty to basically introduce Merwade sir. He is working as a professor in School of Civil Engineering at Purdue University. Merwade sir received his Bachelor of Engineering in Environmental Engineering from Shivaji University. We are very much proud that Merwade sir is alumni of our university. He did MSc in Engineering Hydrology from the National University of Ireland, Galway, Ireland in 2000. PhD in Civil Engineering from the University of Texas at Austin, USA in 2004. His research and teaching interests include surface water hydrology with specific focus on flood modeling and mapping, Much of his work has been on improving the simulation of hydrological processes for flood prediction by using GIS, data-driven techniques, and advances in cyber infrastructure. He has authored more than 80 peer-reviewed journal articles and conference proceedings in the area of river channel, watershed hydrology, and flood modeling. Some of his awards including the Outstanding Achievement Awards 2018 from the Indiana Water Resource Association for work related to flood prediction and mapping for Indiana streams. Excellence in GIS Award he has got in 2017 from Indiana Geographical Information Council for soil-based floodplains map for Indiana, and Quentin Martin Best Practice Paper he has got in 2011. Dr. Merwade sir also disseminates his educational material as online tutorials as well as videos, and tens of thousands of students, faculties, as well as working professionals, they are using this material. So I should now clear the desk for the Merwade sir, and I request him to start his session. Thank you, sir.
Thank you, Professor Panhalkar. So it is always my pleasure to participate in all the activities that Shivaji University takes, and I'm happy to share some of the work that we have been doing in the area of floodplain mapping and modeling. I see many familiar names in the participant list, so good evening to all of you. So the topic of my talk is addressing the flood mapping challenge through integrated modeling and data mining. So the question that we want to ask is flood mapping really a challenge? And if it is a challenge, what makes it challenging? So that's what I will try to address in my talk. What I also would like to do is I would like to, instead of going into too much technical details, I would like to just give you a flavor of some of the work that we have been doing, and we can follow later if there are more technical questions related to our. Can you hear me?
Yes, sir.
Yeah,
yes.
Yeah.
Yes.
So before I get started, I would like to acknowledge all the people and the support that we have gotten to do this work. So this is a list of students who have graduated from my group and the students currently working in my group. So they are the one who do all the work. So my job is sort of messenger. So I just disseminate all the great work that my students do. All the work that I'm going to present to you today, it's been supported by the U.S. National Science Foundation. So this is a research organization that funds a lot of fundamental research in the U.S. Some of this work is also supported by Indiana Water Resources Center and obviously Pardue University, where I work. So before I get into the work that we do, I just want to show what kind of information we have related to water and flooding in the US. So what you see on the screen is USGS. So USGS stands for United States Geological Survey. So what you see here is a national water dashboard. So USGS maintains a network of, this should be 8,500 gauging stations, not 85,000. So there is a typo here. So around 8,500 gauging stations. Sometimes they are close to 10,000. So what you see here are all the stream flow gauging stations. They give real-time stream flow information at all these locations. So you can see, depending on the color, we can find out where the river flow is high. If it is dark green, we are experiencing high flow at that location. If it is red, then the flow is at the low level. So we have about 8,500 stream flow gauging stations that give us near real time, so 15-minute interval stream flow information at all these locations. We also have similar number of weather stations. So these these weather these weather stations are maintained by National Weather Service. So again, the color coding that you see on this map tells you where we are experiencing rainfall. So white means there is no rainfall being recorded at that location, and green and yellow means heavy rainfall, and brown and red means little rainfall but still rainfall. So you can see I prepared this 2 days ago, so you can see the eastern part of US was experiencing rainfall, and most of the western part of US right now we are experiencing very dry spell. So you can see in near real time where we are getting rainfall and how much rainfall we are getting. The weather data is also supported through NEXRAD radar system. So we have about 160 NEXRAD stations. So they cover most of the US. And again, on this map, you can see, I don't know if you can see my cursor. Can you see my cursor? If not, I will change it to...
Yes, sir. Yes, sir.
Okay, I will change it to laser pointer also. So you can see we are getting some rainfall here from the NEXRAD Doppler. So the NEXRAD also covers the entire US. So the weather stations that we have on the ground, they give us very good, accurate temporal information about rainfall, and NEXRAD sort of gives us dynamics of all the rainfall that is taking place in the US. That's all about the weather and near real-time water information. So the flood-related information that we have in the US comes from FEMA. So FEMA stands from Federal Emergency Management Agency. So what you see on this screen are counties. So in India, we have districts. So in US, we have counties. So these are all the counties where the FEMA has created flood maps related to 100-year and 500 return period. And all of these are static maps. So if there is going to be flooding tomorrow, these maps don't tell you about that flooding. It just tells you what areas are under risk from the 100-year and 500-year return period flood. So these are heavy floods. So these maps are usually used for regulatory purposes, mainly for buying flood insurance and regulating flood-related information. Recently, the National Weather Service, or also NOAA, which stands for National Oceanic Atmospheric Administration, so they have developed what we call a national water model. So this is a hydrologic model for the entire US, and this gives near and medium and long-range forecasts for all NHT. So NHT stands for National Hydrography Dataset. So these dataset includes all the streams in the US. So the map that I showed you earlier from USGS that included 8,500 gauging stations, the output that we get from National Water Model, it covers 2.7 million streams in the US. So 2.7 million in India, we can say 27 lakhs of streams. So we get near real time flow information and also flood inundation information from all those 2.7 million reaches from the National Water Model. Recently, a new data set has come up. So this is from the Flood First Street Foundation. So they have used a 2D model called Flood FP. And we have flood risk information for each of the counties in the US. So what you see on the screen is if the circle is big, so more population or more property in that county are at risk from flooding. And if you see counties where you see small drops, then fewer properties and fewer people are at risk from flooding. So this is the sort of infrastructure that we have in the US with related to data that you can get about water, about weather, about flooding. And this is all public domain data. So anybody can access these data sets to get information about what's happening related to flooding and water in the US. So you can see that getting all this information is not an issue, at least in the US. So most of the talk that I'm going to do today is related to our work in the US, but some of it is related to what you may want to do in the future. So getting this information is not an issue. The problem is that the information that we are getting is not accurate. It is accurate at some location, but at most of the locations, it is not accurate. The other issue that we have is that especially the flood maps, so these are static maps. So as I mentioned, if there is going to be flooding tomorrow, nobody can tell what areas will get flooded. So we can go back to our 100-year flood map and see who is at risk. But these days we are getting severe flooding, and that flooding goes beyond what is mapped by FEMA in their 100 and 500 return period inundation zones. So what we are trying to do in our research group is to improve the science of flood modeling and flood mapping. So those of you or many people who are interested in these topics, who want to map flood inundation for their areas, they always ask me these questions. So what model should we use? Should we do one-dimensional modeling or should we do two-dimensional modeling? So I will talk a little bit about our work and what we found from that work. Many people also ask, should we use a loosely coupled model and tightly coupled integrated model? So those of you who are not familiar with this integrated modeling, or we call it here as H&H modeling. So H&H stands for hydrology and hydraulics. So hydrology basically converts rainfall into what is going to go into a river. So how much water will go into the river. And hydraulics, we use hydraulic model to find out what happens to that river when it enters that river. So the actual flood inundation map comes from a hydraulic model, and the water that goes into hydraulic model comes from hydrology. So most of the times these two are handled separately. So people run hydrologic models to get the flow, and they use that flow in a hydraulic model to get inundation extent. So we have been doing a lot of work exploring this loosely and tightly coupled approach, and I will talk about what we found. The other issue that we have from this flood map, so even though the data is available for the whole US, some of that information is not really locally relevant. So especially in urban areas, we are experiencing a lot of flooding these days. So if you think of an urban area, it has a lot of infrastructure. So there are stormwater pipes, there are bridges, there are culverts. A lot of this information does not get incorporated into these big national scale models. So when they give predictions, so that's why those predictions are not very accurate, and they're not really relevant to what is going to happen when we experience flood in urban areas. So I'll talk a little bit about that. And then finally, if we are doing all this work, how do we communicate all this information to public? And as I mentioned, a lot of this information is not accurate. So there is a lot of uncertainty involved. So how do we capture that uncertainty, and how do we communicate that uncertainty to general public? So these are sort of areas that I will topically cover in my talk, and if there are more technical details, we can follow up later. So let me just talk about comparison of 1D and 2D hydrodynamic modeling. So again, those of you who are not familiar with this topic, so when we do one-dimensional modeling, we assume that the water is flowing in just one direction, and when we do two-dimensional modeling, we assume that the water is flowing in two directions. So when you think of floods, you will know that water flows in two-dimensional domain, not just 1D when we have flooding. The question then is, should we use a 1D model or a 2D model to simulate that flood? So we did a study, we have done several studies. So I'm just going to show you results from the recent work that we have been doing. So what you see on this map are few areas in the US. So there are 4 different locations. So 2 of them are in Indiana. So this is Indiana. This is where we are based. So Pardue University is here. So we have 2 data sets from Southern Indiana, and then we have some data sets from the state of Arkansas. So if you look at these rivers, you will see that some of, so for example, this Flat Rock River, you can say that this is relatively straight. White River, you can see it's a meandering river, and for the Arkansas region, it's a mix of both straight and meandering rivers. So many people who say that we should use 2D model for complex river system. We wanted to use rivers of different geometries, different configuration to evaluate whether 1D model will give us better results or 2D model will give us better results. And the blue area that you see around these rivers, so these are actual flood extents for a historical event. So we wanted to see our modeling can produce these extents and how well we can capture these extents from these different models. So this table again just shows the properties of these reaches and the data sets and the data that we use. So the date that you see here in the table at the bottom, so these are real events. So we wanted to simulate these actual events and see how good these models are in predicting and giving us the inundation that will match the actual inundation. So I'm not going to go into all the details of the models that we use and the physics of those models. So what you see on this slide is just a methodology. So we set up the model, and one of the parameters that play a major role in all models are the parameter values. So for example, in flood inundation modeling, the roughness parameter, or those of you who are familiar with Manning's equation, there is a variable Manning's n. So that Manning's n plays a critical role in setting up a hydrologic model and getting an accurate simulation. So what we tried to do here was we used 4 different models. Some of them, or 3 of them, were 2-dimensional. 1 of them was 1-dimensional. And then we changed Manning's n and see how these models react and whether they are able to produce the actual inundation that was observed for these events. So without going into all the details of what models we use and all that, so what I'm going to show you on this slide, so you see sort of 4 columns. So H1 stands for HECRAS. So those of you who are familiar with HECRAS, so H1 is 1-dimensional HECRAS, H2 is 2-dimensional HECRAS, and LD and LS, so these are list flood versions. So the map that I showed you from First Street Foundation for the US, that was created using list flood. So in this matrix, the first column is 1-dimensional and the last 3 columns are 2-dimensional. If you see a lot of blue areas, it means that the model is simulating that event accurately. If you see a lot of yellow area, that means that the model is underestimating. If you see green area, you will see that the model is overestimating. So what you see here are simulated inundation extent for Manning's n value for the main channel of 0.03. And if you look at these maps, you can see that there are some differences, but they are not very significant. So for example, if I look at this data set, you will see that all models are giving more or less same results. Actually, the 1-dimensional model is giving better result than some of the 2-dimensional model that you see here. Same in this case. So you can see there is a lot of underestimation from the 2-dimensional version of HECRAS, and the 1-dimensional of HECRAS is giving us good results as well. So we did that for multiple and I'm trying to move my slides. So we did that for multiple Mannings, and what you will see, and I'm not going to explain all these images again, I just want you to glaze over these maps and see if you see significant differences. And you will see that, yes, there are some. So for example, here you can see this is doing much better compared to this one-dimensional. But for most of the other simulations, the 1D model gives us equally good results compared to the two-dimensional model, and same for another Manning's N. So actually, again, you can see, so this is a two-dimensional model, this is a one-dimensional model. You will see a lot of underestimation from a two-dimensional model compared to a one-dimensional model. So if we are asking this question, whether one should be using a 1D model versus a 2D model, so these days, a lot of people are hyped about two-dimensional modeling. So everybody wants to use the latest and the best model that is available, and these are two-dimensional model. So what we have found, and this is just a single study from multiple studies, what we have found is that the model performance is not significantly affected whenever we are using a 1D versus 2D. So the main parameter that plays a significant role in creating a good simulation from either a one-dimensional model or a two-dimensional model is Manning's N. So if we use the right combination of channel and floodplain roughness, 1D and 2D models can give equal results. Now, this is true if we are interested in flood mapping and flood inundation modeling, because these are very high flows. So what we have found for these high flows is that 1D and 2D can give equally good results. So we really don't have to go into two-dimensional modeling. Now, if you are really interested in the hydrodynamics at very fine scale, then you may find some differences between 1D and 2D. But for most flood modeling and mapping purposes, we are good with 1D model. So the next question that I'm going to address is, so the results that I showed you, they were from loosely coupled. So we simulated only the hydrodynamics. The flow was obtained from USGS gauges. But many times when we are interested in near real-time flooding or forecasting, we don't have flows. So we have to simulate those flows and use those flows in a hydraulic model. So these days, and historically, this has been done in a loosely coupled approach. So the flow is obtained from a different model and it is then used in a different hydraulic model. So what we have been propagating for last few years is perform integrated modeling of hydrology and hydraulics to improve flood simulation. So to answer that question, what we did was we used models of different complexities. So I'm going to show you three configurations here on these slides. So the first configuration, I'm going to call this as C1. So C1 is what I just showed you. We input flow in a hydraulic model and we simulate that flow to get inundation. So when we do that, what happens is that model is not actually interacting with impervious, or it's not interacting with the subsurface, it's impervious to subsurface. And the flow that we get is from a different hydrology. Maybe the host can mute the participants if that is possible. So when we have high flood, you can also expect some rainfall in the floodplain. So these hydraulic models, they don't incorporate rainfall in the area that they are simulating. So the second configuration that we have, it addresses some of the issues with the first configuration. So now we have rainfall, we have also subsurface interaction, but we are not really capturing the deep groundwater flow that may also be contributing to some of the water that you experience during flooding. So many times when I talk to people who experience flooding, they some of them also mention that the water actually started coming from under the ground before it even got on the surface. So that's where the subsurface part comes into the picture. And the final configuration that you see here is the C3. So C3 configuration is a complete integrated model. So it integrates hydrology on the surface, on the subsurface, deep groundwater, and it also incorporates all the hydrodynamics, detailed hydrodynamics. So we wanted to see how C1, C2, and C3 will perform in giving us a good or accurate simulation of flood flow and also inundation. And again, to do this, kind of studies, you need historical data. So what we did was we used actual event. Yes, so now there are not many models to do this kind of integrated approach. So we have explored many models. So one model that fits our criteria to perform this study is called ICPR. This is a proprietary model from Streamline Technologies. So we have sort of collaboration with Streamline Technologies, and we work with them to develop and use this model for our research. So again, those of you who are familiar with this topic, what you see on this slide are different processes and different data sets that are used in the model. So we have the surface part, we have the subsurface part, and we have the aquifer, the groundwater part. So overland flow, Vedos zone, groundwater, and then you need data from all these. So the data that you see in these boxes, so topography, roughness, if you are going to incorporate subsurface, you need to have information about soil. If you are going to incorporate groundwater flow, you also need to have information about aquifer and all that. So this is an integrated model. It starts with rainfall, and what you get at the end is a dynamic flood inundation map. So this model can actually tell you when you can experience flood, at what location, and how deep the water will be. So that's the kind of information that you get from this model. So this is the study area that we use. So again, this is Indiana. So this is the upper Wabash River Basin. So Indiana is mostly agricultural region. There are few urban areas. So the red areas that you see here, these are all urban areas, and everything else is agricultural. So the yellow part is agriculture, green is forest, and red is urban. So to create this model, so we used LiDAR topography, we used information from all the available gauges and weather stations. And one of the things that we did in this was, since this is an integrated model, the idea is that if you use the right input, the correct input, you don't have to do any calibration. So again, those of you who are familiar with modeling, your model cannot really give you good results unless you calibrate it. So the good thing about using a good model is that if your input data is good, then your output should also be good and accurate. So there was no calibration involved in this study. So what you see on this slide are hydrographs. So again, those of you who are not familiar with what hydrograph is, so this is time on x-axis, and that's the flow on y-axis. So that's the amount of water that is flowing through these locations where we have gauges with time. So when you have rainfall, when you have flood, it will peak and then it will go back to the normal flow. So the red dash line that you see here, this is the observed hydrograph, and the blue, red, and green line that you see here, so these are the simulated output. So C1 was the simplest configuration, so you can see it overestimates our peak. C2 was a better configuration compared to C1. It gives us a good peak, but you can see it underestimates all the low flow, and that again has to do with it does not incorporate the subsurface part completely. And C3, which is a complete integrated approach, you can see that the output from our model matches perfectly with what was observed. So again, the idea here is that if we input correct rainfall amount into this model, it will accurately tell us how much water we can expect in our stream and what time the peak will occur. And if we get that kind of information, then the hydraulic part will give us the inundation part. And again, these are just numbers. So those of you who are familiar with model, we are always interested in looking at what the R square is, what the NSE is, and so on. So if these values are close to 1, so 1 is a perfect match, and you can see the values that we are getting from C3 they are close to 0.95. So you cannot get any better than this, and so we are very happy about this. And then what you see here is the inundation area corresponding to those peaks, and I will also show you those maps. So when you do this kind of studies, one can come back and say, okay, it worked for your area, will it work in other areas? So when you do this, you always have to validate at some other location. So this is Indiana state. So this is where we are mainly agricultural. And this is New York, which many of you are familiar with. So in New York, you have a very different topography, very different land use. So what we did was, if it works in Indiana, which is agricultural, and if our model is good, if the input data is good, will it work in a very different location? So we did that, and you can see again that the R square and NSE, they are again very close to 1. So what this shows is that the model that we are using can give us good results at any location if our input data is good. And once you have the flow accurately predicted, then you can use the hydraulic model to map the inundation. So what you see here is the inundation corresponding to this peak. And again, this was an actual event from Hurricane Irene in 2011. And we were able to map the inundation very accurately by using this model. So the question that we were trying to ask was, will integrated modeling give us good results? And the answer is yes. So the current practice that we use may not provide realistic flood inundation information, but the integrated model will give us very accurate information. The question then is, right now what we have done is we have tested it at individual watersheds. So for example, if you want to implement this for the entire state or even for the entire US, for a country, will it work? So the issue of spatial scale. So when you change the scale, will this model stand up to that configuration? So that's the question that we are going to answer in our next few slides. So what we did here was we created the model for at different scales. So again, this is one basin. So what we have here are multiple locations where we have gauges, and we simulated the model for these watersheds. So some of them are small, some of them are big. And this is the integrated model that we have. It has it works on a finite element mesh. So what you see on this table are S1, S2, L2, L4. So S is for a smaller version of the model. L1 is the larger scale model. And then whether we are using integrated, and then we have two different resolutions. So we have surface water, and that surface water is interacting with groundwater. So the size of the finite element mesh that you use for surface water and for groundwater, that is going to impact your simulation. So what we tried to do here was, again, if you ask someone what mesh you want to use, the answer that you will get is you should try to use the finest mesh possible to get accurate results. The issue with that is that if you use a very fine scale model, it comes with a very high computational cost. So what we tried to do here was try to figure out a scale that will give us good results for the surface and subsurface. So the two models that I would like you to focus on are this L2 and L4. So L2 has both surface and subsurface at very fine resolution. L4 has surface at a fine resolution, but the subsurface or groundwater at a very coarser resolution. So the idea, again, if you think about it, is that on the surface, water moves very fast because there is no resistance, but within subsurface, the water is moving through soil. So the water movement is very slow in subsurface. So there is no point in using a very fine resolution mesh mesh if you're trying to simulate that slow movement of water. So that's why we used a coarser resolution mesh for subsurface and see what kind of results we can get. And these are the results. So again, as I mentioned at the beginning of my talk, I'm not going to go into a lot of technical details. So this work that you see here, it's been going on for last 10 years. So I cannot cover everything in 1 hour. So I'm just going to give you flavor of what we found, and hopefully some of you will find this useful. So what you see on this slide are results from L2. So L2 again is using a very fine resolution for both subsurface and surface. And the results that you see here, so there are 3 rows. The first row is a small scale model, and as you go down, the scale of the model increases. So you can see that for a small scale model, the fine resolution surface and fine resolution subsurface is giving very good results. But as the scale increases, you can see the model is not giving us very good results. So that's the L2. And then with L4, you can see that as the subsurface mesh becomes coarser, the model improvement is significant. So again, you can see the NSC jumped back to 0.9. It was 0.69. Now it is 0.9. So the model improved significantly when we used the appropriate scale for simulating the behavior of subsurface and groundwater flow. Again, same results with a different view. So the idea is R square and NSC. So the blue column that you see here, that's our L4, and you can see it's close to 1 for all of this simulation. The bottom 2 plots are about error. So error, you want the lowest. So again, you can see the blue column has the lowest error among all the configuration. Again, when you do this, the question again is, will it work in other areas at different scales? So again, we validated this for a very urban area. So this is again Indiana, and Indianapolis is the capital of Indiana, and you can see it's all urban. So red means all urban. Will it give accurate results? So again, these are the results from L2. You can see the red is the model output. It's not matching with what was observed. With the L4 version, a different mesh for surface and subsurface, the model is predicting very accurately. So again, that's the kind of information you want to get if you want to alert public about how much water we can expect in our stream and how much inundation it will cause. And the map that you see here in the middle, that's the flood inundation map. So with the traditional approach, most of the times you get information about inundation along the river. You really don't get information about inundation in residential areas and areas where you don't have any river or stream. So with this integrated approach, you can get inundation information at any location that you want. So again, coming back to that question, can integrated model be used for flood simulation at a larger scale? And again, the answer is yes, if we use the right configuration of our mesh for surface and subsurface. But there is always a but for all this. It's computationally not cheap. It takes a lot of computational power, and it takes a lot of time to run this simulation. So how can we improve the efficiency of this model when it comes to computational power? So on this slide, I again want to show you the difference between the loosely coupled approach and the tightly coupled or integrated approach. So on the left, this is the output from a loosely coupled model. So you get inundation along the river and areas near the river. With integrated model, you get inundation everywhere, regardless of whether you are close to river or away from the river. So as I mentioned, to do this, you need a lot of computational power, you need a lot of data. The question again is, how can we improve the efficiency of this model when it comes to computational power? So to do that, what we are calling here is called objective-oriented hybrid flood modeling. So the idea here is that you use a very fine scale, very detailed model where we need information, and then there are a lot of other areas where you don't have a lot of people or infrastructure, and you may not need a detailed flood inundation information or flood inundation map for that area. So we are going to use a hybrid approach. So detailed modeling where we need it, and coarser modeling where we don't need it. So again, these are again different regions in India now where we are going to test our hypothesis. So in hybrid approach, it's not just about mesh. So earlier we spoke about fine resolution mesh versus coarse resolution mesh. Even the methods that we use to simulate the hydrology and hydrodynamics, there are so many methods available. Some of them are empirical, some of them are physically based. And when we use physically based approaches, they need data, they need computational power. If you use empirical approach, they can be much faster. So in a hybrid approach, what we are proposing here is not just use different types of mesh, but also use different types of methods to simulate the surface and subsurface part. And the mesh that we set up again, so this is area, an urban area where we need detailed flood information. Everywhere else we don't need. So you see a fine resolution mesh at the areas where we need that information, and everywhere else you can see we don't have a very fine resolution mesh. Actually, we don't have any mesh. We are just interested in finding out how much flow we are going to get from these areas, because again, these are all agricultural areas. If they get flooded, it is fine. All you need to know is how much water is coming from that area. As I mentioned, we are not just, when we say hybrid, it's not just about playing with the computational structure of the model, but also the methods that we use. So again, those of you who are familiar with this topic, you may recognize some of these names. If not, it's fine. So I think Darcy law, Brooks and Corey equation, and some of this it's taught in many undergraduate courses. So hopefully some of you are familiar with this. So again, these are the times. So you can see you get a lot of computational efficiency when you use hybrid approach. So we can come back to those numbers if needed. So again, these are the hydrographs. So you can see our model is matching perfectly with what was observed. So the NSE values are very close to 1. So again, as I said, you cannot get any better, or actually it's impossible to get these kind of numbers with many models that are used for hydrology and hydraulics these days. So with hybrid approach, as I said, we want inundation in where we are interested. So you can see this is giving inundation for the entire watershed. With the hybrid approach, if we say we want just inundation along this area, we can get that. And F statistic, again, this is the index that we use to match with what was the actual inundation. So if F statistic is close to 100, it's a perfect match, and you can see we are getting 0.94. So you cannot again get any better than that. So more results. So again, just to show you that the results that you get through this approach is accurate, and you can accurately simulate and predict the hydrograph and eventually the inundation. So when you do this, this is the kind of output you can expect. So as I showed you earlier, this is the area where we had the integrated model. This is where we have the sort of hybrid approach. We don't need the inundation at this scale for these areas. So where we need it, we have this dynamic near real-time inundation. Where we don't need it, all we get is the flow, and then we simulate the flood along the main channel or main river. And eventually, actually, after you do all this, this is what we want, the maximum inundation. If you use the integrated approach, you will get the inundation extent everywhere, but this will take a lot of computational power and a lot of time. But with the hybrid approach, you get the detailed information where you need it, and everywhere else you can see it's sort of blank. Again, you want to validate this, and we did the validation and we got equally good results. So again, if we come back to the question, is it good? Yes, it is good. But can it simulate complex systems? So many of the watersheds that we have used, they are not complex. So complex in the sense, if you think of a very urbanized area, and I think when we think of flooding these days, there are a lot of urban areas where we get a lot of damage. When you think of urban areas, we have a lot of urban infrastructure, stormwater network, we have bridges, we have culverts, we have all sort of infrastructure. Many of the models that we use today are not able to incorporate these infrastructure. So the question is, can we incorporate this kind of infrastructure in an integrated model and create an accurate simulation? And we try to answer that question by using the example of Hurricane Harvey. So some of you may have heard about this event in 2017 in Houston, Texas. So we got about 30 inches of rainfall in less than a week. So 30 inches. So again, many of you are from Kolhapur. So the recent flooding in Kolhapur, we got 10 inches of rainfall in few days. So this is more than 30 inches of rainfall in few days. So you can see it was a very huge event. So the question was, can the model that we are trying to use simulate that kind of event and give us accurate information? And this was in Houston. It's a very urban environment, and we wanted to incorporate all the infrastructure that we have in that urban environment and see if we can simulate that. As I said, it's an urban area, so a lot of red, and then you see some agricultural and green around the suburbs, but the main city, it's all red. We are sort of running out of time, so I will not go into all the technical details of the mesh size and all that. So as I mentioned, it's a complex model. So the type of information that we have incorporated here, so you can see we have incorporated all the road networks. So with road network comes bridges, culverts, and all that information. This is the Houston International Airport. So all that information is incorporated. So this is the stream or channel flowing through that area. So we have incorporated the cross sections, detailed cross sections, and all that. Even if you use LiDAR data, so these days many people want to use LiDAR for inundation mapping and hydrologic modeling. Even the LiDAR data does not tell you what's under the river. So we have tools to incorporate that kind of information, because if you want to do accurate simulation, you want to make sure that you represent your rivers accurately. So we have those kind of tools. So we run the simulation. So again, I'm not going to go into all these numbers. This is the kind of results you can expect from this. So again, a dynamic simulation telling you how much flooding will occur at what location and at what time. So this is the dynamic simulation coming out from that model. So there are two reservoirs here. So you can see they fill up and then the water starts flowing downstream. And if you just want a static map corresponding to the maximum flow, this is what you see on the right. Again, same with the hybrid, with the smaller scale model. So you can see the reservoirs are filling now. And once the reservoir fills, the water will start flowing downstream, and you will see the areas getting inundated. After we did this, we wanted to see how accurate our model is in simulating and predicting the depth of water, because that's what eventually matters to general public, how much water will come into my house or into my building. So many agencies in the US, when they have this kind of flooding, they go and measure how deep the water was. And what you see on the bottom right here is a histogram that shows how much error we got in our inundation depth corresponding to what was measured. So you can see more than 60% of points that we estimated, they have an error very close to zero. So our inundation depth at different locations, or at least 60% of the points were predicted very accurately. Then there is 20 to 25% where our error was within 1 meter. So Then we compared what was actually observed through images and where our model predicted. So I'm not going to go. So again, just to show you, this is what was observed, and these are the areas where the model says will get inundated, and they were inundated for that event. So again, just different images and different inundation map. So eventually, if this works, where we want to go with this is creating a model for the entire state of Indiana and eventually for the whole US. And when you have an event, then you can expect output something like this. So it gives you how much water is flowing, where it is flowing, and what areas you can expect. So the area that you see here is about 85,000 square kilometers. So it covers the most state of Indiana. We continue to do this work. So when we think of urban, the urban infrastructure never ends. So we have stormwater pipes, we have all kinds of infrastructure. So we continue to modify and improve this model. So the final thought is that integrated modeling is good. It can give us very accurate results, but it's very complex. So we have to optimize the computational speed, prediction accuracy, and the resources that we have available. Then the question you may ask is, if we don't have all that resources, if we don't want to do that kind of complex modeling, can we get away with the simple model? And the question is yes. With simpler model, as I said, they are not accurate, but they have a lot of uncertainty. Then the question is, can we simulate or predict what that uncertainty is, and can we incorporate that uncertainty? So that's what I'm going to show you next. So what we have done here is we have used a simple loosely coupled approach and tried to incorporate the uncertainties. So what we have done here is we used an approach called Bayesian model averaging. So you basically run hundreds of simulation using different scenarios, and you come up with an ensemble. So the gray area that you see here are results from hundreds of models, and then you create a mean from that. And then when you create the mean, the black line that you see here is the observed. The red line that you see here is the mean of the ensemble mean of all the simulations. And you can see that the ensemble mean that we have from this BMA matches again very well with observed. So even without doing the complex modeling, if you can use a simpler approach, but if you incorporate the uncertainty, you should be able to create a reasonably good model. And when you do this kind of modeling, what you end up is with a probabilistic flood inundation map. And this is again something that I have been advocating for a long time, is that we should not be using a single flood inundation map. So the idea here, so again, the term that people in India use is the red zone. So red zone is not a single line. What that tells you is that if you are inside that zone, you are at flood risk. If you are outside that zone, you are not at risk. And that's not true. So we cannot really tell exactly where the flooding will occur. So what we have been advocating for a long time is a probabilistic flood inundation. So yes, as you are closer to that red zone, you are at higher risk, but as you go away, your risk decreases, but you are not completely safe from flooding. So this is something that we have been advocating for a long time, is that we should be using probabilistic flood inundation map, not just the single line. Now, all this modeling and getting data and all that, it is all complex, it takes time. The question then is, can we use simpler data-driven approaches? And I think these days there is a lot of interest in using machine learning and artificial intelligence for predicting flows and simulating floods and inundation extent. So we have been doing that kind of work too. So what you see here again is the Ohio River Basin. So the US is divided into what we call hydrologic units. So we call them HUC. So these are the maps corresponding to HUC2. So as you increase the number of this HUC, the scale reduces. So what we are trying to do here is use all the gauges that we have from USGS and create a machine learning model to simulate flow at smaller reaches. Again, these are all the details of the data that goes into the machine learning model. These are the stations where we are testing and validating the model, and these are the results. So again, what I want you to focus on here is that this is the NSE. Remember, if the NS is close to 1, the model is very accurate. And so you can see the output that we are getting from this machine learning model. In some areas, it is close to 8, which again is very good. So until now, I have shown you NSE values close to 0.9597. And as I mentioned, they are not very easy to get. They are almost impossible to get. So even if you get something close to 0.8, we should be happy. And you can see that we are able to get something close to 8 at the HUC6 level. So HUC6 is a smaller scale. As the scale increases, the performance of this machine learning model decreases. So we are looking at ways on improving this accuracy. Again, same results shown in a different way. So for the HUC6, you can see all our NSE values are high. For the HUC6, for HUC2, they are all over the places. In some locations, they are close to 1, but at most of the other locations, they are lower than where we want them to be. So we are working on improving that model. Eventually, then we also want to use machine learning approach to map the inundation, not just get the flow. So that's, again, these are all preliminary results. So to do that, you need information on historical flood inundation. So we are working on developing tools and also checking which tool will give us good inundation that we can extract from aerial images. So what you see here is inundation extracted for the state of Indiana from Sentinel images. So this is again ongoing work. The other thing, and this is the final work that I would like to share with you, is that communicating information about flow. So we are calling this urban flooding open knowledge networks. So these days, if we want answer to any questions, we just Google that question and we get answers. So what we are trying to do here is create Google-like infrastructure for getting flood-related information. So when we think of flood, it affects everything that we have in our cities. So what you see on the right are all the infrastructure that we have in cities. We have power grid, we have sewer system, we have hospitals, we have reservoirs, we have surface water, groundwater, drinking water, transportation, and these are all connected. So many times people ask, why do we lose water supply when there is flooding? Because the pumping station may have gotten flooded, it may not be working, the roads get blocked, people cannot go from one place to another. So what we are trying to do here is capture all these cascading effects and create a knowledge graph. So the question is, if you ask what will happen if there is a flooding here, it can tell you what roads will be closed, what pumping stations will be down, which areas will lose power, and all that. So we are trying to develop that kind of infrastructure to answer questions related to flooding. And people could use different apps and ways to answer that kind of question. So what you see here is a person asking a question, how do I go to my office if there is flooding? So it will show him or her the route, safe route that he or she can take that is not flooded. Emergency manager may ask what areas in my city are at risk, and people may even ask if I should buy a house in this area, is it safe from flooding? So those kind of questions we should be able to answer if we build this knowledge graph. So this is just the summary of everything that I spoke. I was also asked to talk about Kolhapur flooding, and I will spend just a few minutes after this slide. So as I mentioned, 1D modeling can give us reasonable approach for mapping flood inundation if you are interested in high flows. So for low flows, the answer may be different. Integrated modeling is complex, so we should be using If we cannot do integrated modeling, we can use simpler models as long as we incorporate uncertainty. And data-driven approaches also have potential to improve flood forecasting if we don't have access to all these complex models. And we do all this work. The key again is, can you communicate this information to general public, and can they use this information in a way that is useful to them? So that is the key for mitigating flood losses and improving resilience. So finally, I will just give my thoughts. I would like to say that I have not done a lot of work on flooding in Kolhapur, although I would like to. So these are just my thoughts and opinions, and hopefully you will find them useful. So what caused flooding in Kolhapur? So depending on who you ask, you will get different answers. Some people will say it's all this haphazard development of the city. Some people will say some reservoirs are not being managed properly. There's backflow and all that may have caused flooding. Some people will say there is too much silt, and I think the word that people use is the gar. We should remove gar from all our rivers so they can flow easily. Some people will say there is lack of stormwater management. We don't have enough infrastructure to move all this water. Some people will say climate change. And then you may have heard lots of other rumors about why we got flooding in Kolhapur. If you ask me this question, and I would say all of above, the problem again is that some of these, for example, haphazard development, improper management, too much silt, lack of stormwater management, they will play a role in increasing the risk from flood. But when you get that kind of rainfall that we got, any of this will not help you. So when you get too much rainfall, if it's just the question we should be asking is, when did the last time we got this kind of rainfall? And if you think about it, Kolhapur flooding is not an isolated disaster. Actually, Kolhapur has experience in flooding, and actually these days there are several areas all around the world that are experiencing flooding that they have never experienced in their lifetime. So at least I remember that we had flooding around 1989, 1990 in Kolhapur that was severe. And then I left Kolhapur in around 1998. So I think we also had flooding in 2019 and now in 2021. All I want to give you is some information so you can put this in context. So this is, again, the number may not be exact, but I don't think I'm too far off. So that's the amount of rainfall we got in Kolhapur in 2021, in I think end of July or beginning of August. 250 millimeters. So we use inches here in the US. So that's close to 10 inches of rainfall in 2-3 days. Just a week before that, there are areas in Germany that got 200 millimeters of rainfall, and these are the areas that they have never seen flooding in their lifetime. So there was 200 millimeters of rainfall in 3 days. Around that time, there was flooding in Zhengzhou city in Henan province in China. Look at this number, 200 millimeters in 1 hour. So this is the same amount of rainfall that Kolhapur got in few days. That rainfall took place in 1 hour, and you can imagine what kind of havoc you could get if you get that kind of rainfall in 1 hour. And it was 620 inches in 3 days, so almost 3 times than what Kolhapur got. Closer to home, here in the US, so Nashville, Tennessee got 450 millimeters, so twice as much as Kolhapur in just a day. And then finally, you may have heard about flooding in New York. So you can see the number is not very high, but again, New York has never experienced this kind of rainfall in the recent history. So what we are experiencing everywhere around the world are these historical proportion of heavy rainfall. And any infrastructure that we have is not designed to deal with this kind of rainfall. So when we talk about silting, when we talk about infrastructure projects and all that, so these really don't matter when you get this kind of rainfall. So the question that we should be thinking, and I'm glad that the Shivaji University took the initiative to create the Climate and Sustainability Center. And these are some of the questions to think, and hopefully this will help the city to make more resilient to flooding. So what I mean by that is that we cannot expect that we are not going to get this kind of flooding in the future. Actually, we should expect that we are going to get this kind of flooding. The question is how often, when, and how much. And to answer that question, hopefully some of the modeling work that I showed you may find that useful. And by making more resilient, what I mean is that we are going to experience this kind of flooding in the future. The question is, how can we mitigate the losses from this flooding, and how faster or how sooner can we recover from this flooding? So these are the questions. Again, there are many more questions, so maybe these are something to think about. So with that, I will stop. You will find information on how to get in touch with me on this slide. And I don't know if we have time for question and answers, but I'm happy to stick around for a few more minutes if anybody has any questions. So with that, again, I'm thankful to Dr. Panhalkar and Shivaji University for giving me this opportunity. I hope some of you found this information useful. So with that, I'll stop and thank you.
Thank you, sir. It was a really excellent session. In fact, you have talked that when we are talking about the modeling, what kind of challenges we are facing, what is the difference, what kind of result we have when we are going to compare 1D model and 2D model. That also you have shown. You have also shown the accuracy of the integrated model. And various participants, they have raised certain queries I would like to put in front of you. First of all, we will take the question answer session for a few minutes, and few questions we will take. One question we have got from Somnath Pawar sir, that can we use subset selection approach in integrated models to reduce computational and data costs?
Yes, the answer is yes, and that's what I meant by the hybrid modeling approach. I hope that's what you mean. Yes, so you simulate areas where you want detailed information by using a completely integrated approach, and in other areas, then you don't need all that detail. So there you can get away with a simpler model. But what we have found again is that the computational power is still very high compared to you want to just use a simple model. The answer is yes. Yeah.
Another question we have got from Ravindra Mane. Can you prepare a flood model for Kolhapur district, or what kind of challenges would be there?
So if I believe Ravindra Mane is our friend, he is also KIT graduate, and I think he recently graduated from Shivaji University with MTech. Yes, we can, as I said earlier, we can create flood maps anywhere these days. If you have a digital elevation model, you can create flood map also for Kolhapur city. The question again is how good your data is and how detailed you want your flood inundation map to be. So based on that, there are challenges associated with data requirements. So as I said, for the integrated model we did, you just don't need topography data, you need information on soil properties. So when we say soil properties, this is not just one property for the entire area or soil. So the soil data that we have is a gridded data set in the US. So it gives you soil properties at 10 meter by 10 meter resolution. So you need that kind of information. You need geologic properties. So you need accurate rainfall. You need computational power and the model. So yes, these are all the challenges. And depending on what you have, these may all be challenges, or these may some of the challenges that we can easily address.
In that in India as well as in Kolhapur area or in Maharashtra, when we are talking about, we are having the limitations with respect to the data. What kind of data you're talking about, that is the geology or as well as the soil properties, such type of data we don't have. That is 1:50,000 scales. We are using the soil maps here in India. So regarding to that, by considering the models you would like to propose for India?
Yeah, so as I said, if we don't have that kind of data, there is no point in investing in a very detailed integrated model. So there are other models, for example, HMS, you are familiar with SWOT. SWOT will give you simulation at the daily scale, and for the event-based, we can use HMS. And actually, I have a student, I have asked him to now start creating HMS model for the whole US to see what do we get and how we can improve it. So even though I gave you all this information about this integrated model from my research, but we are in parallel exploring what can we get from a simpler model and how can we make those predictions from a simpler model relevant, so we can use that for flood modeling and mapping purposes. So maybe I just want to add, I don't want you to take this message that integrated modeling is the one that we should be using. Yes, it is the best, but if we don't have resources and capabilities, we can use a simpler model and get, I wouldn't say equally good, but reasonably good results as a starting point.
Another question we have, that is from Gaurav Arote. He has asked that what is the impact of sedimentation on flooding? I think with respect to Kolhapur also, you have, I think you have mentioned that point.
So sedimentation will decrease the carrying capacity of a river. And what that means is that, yes, it will increase the water level, it will increase the flood risk, but the risk associated with that and the increase associated with that is more significant at low flows. So for example, let's say the regular flow in Panchganga River, and I don't even know the number, let's assume 100 cubic feet or 1,000 cubic feet per second. So right now, if the river is not, there is no silt in that river, that 1,000 CFS may not bring the water over banks. But if there is a lot of silting, the same 1,000 CFS flow will bring water over bank. It will flood some area around that river, but when you have a very high rainfall event similar to what we got, that increase will not impact significantly what we experienced in terms of flooding. So I'm not sure if I answered his questions or not. Yes, the silting will increase the flood risk, and the risk changes depending on the magnitude of flow. I guess that may be a good answer. So depending on what magnitude of flow you are looking at, the increase in risk from sedimentation changes. So higher the flow, the decrease in the relative risk. So
another question we are having from Adi: how much accurate of SCS-CN rainfall runoff model for urban areas?
It depends. The CN that you get is again dependent on the data that you use for land use and soil. What we have found is that you always have to calibrate that curve number. So it depends on how calibrated your model is. And depending on how good your calibration is and how many events you include in your calibration, you can get a reasonably good result. The other issue with the curve number method is that it does not truly incorporate the antecedent soil moisture information. So there are, again, whoever is asking hopefully is familiar with this. So we have curve number for dry condition, we have curve number for wet condition, and we have curve number for normal conditions. So we have only 3 variations of that, but within that, within dry and wet, you could, there is a lot of variation how dry and how wet is. So what we are trying to do is, how can we use information from satellite to see how wet the soil is and adjust the curve number accordingly, so the simulations that we get from the curve number can be more realistic. So again, that's something that we are also exploring.
Now we are talking about the climate change, and you have also given certain examples that how the intensity of rainfall that is increasing. And with respect to that, when we are using the models like the ArcSWAT in association with HECRAS and all that, what kind of limitations you see?
The limitations, again, I see. So the main driver to these models are these climate inputs. And I don't think we have very accurate projections even about the climate. So the climate projection also change. So until we get our weather forecast and climate forecast right, no matter how good your model is, it's not going to give you very good results. And it is not to blame the model, it is to blame the data that we are inputting into the model.
Thank you, sir. It was a very nice session. All the queries which are being asked by the participants, you have given the answer very openly. And now I would like to request our chairperson, Professor R.K. Kamath, to give his remarks. Kamath.
Maybe he is muted, or I see him muted.
Panhalkar sir, कामत सरांचा बहुतेक तुमच्या एंडला म्यूट झाले, अनम्यूट करा की.
Hello, sir.
Hello. Yeah, now I could unmute myself. Yeah. Yes, can you hear me?
Yes, we can.
Yeah.
Yes, we can hear you.
Yeah, it was a really excellent talk by Dr. Venkatesh Merwade, and thank you very much for such an excellent talk. Because as we know that there are around 2 billion people, because the statistics entails that 2 billion people are affected by flood in last 20 years. So it's really a very important issue to address this kind of natural calamities. As he has already talked so much about the flood forecasting, and recently there is a initiative, AI for social good. So artificial intelligence has been increasingly used for social good. And this is a part of the use of the technology for the societal benefits. He has very much detailed discussion about the indentation model. And indentation model, lot of things were talked about the data. So data, getting the proper data and getting the adequate data is really, really important in all this modeling. Dr. Merwade has talked about so many things. And recently, Google has also come out with a pilot project in this particular direction about the indentation model, wherein the real-time water level measurements have been carried out. And I think there is a lot of scope for IoT, because in the audience, I can see many computer science faculty members are there. From electronics also many faculty members are there. It's really interdisciplinary group. So we should take care, we should have more infrastructure for collection of the data. And the real-time water level measurements are really important. And in this particular aspect, there is a success story from the Indian government, because Government of India under the Indian Central Water Commission, they are measuring water levels on an hourly basis by using strain gauges. Strain gauges are the small sensors, and those sensors, they are really put to use for getting the data regarding the water condition or water level on an hourly basis. So these kind of water level measurements on a real-time basis, this really helps the kind of modeling that Professor Merwade has talked about. And it really helps in getting the inputs for our models. Because if we want that our model should work and it should give the right kind of prediction, then the right kind of data should be given to the model. And then only it is possible to have the successful modeling. What I liked about Professor Merwade's talk is he has talked about many state-of-art concepts, such as the elevation map creation. So recently we also came across some digital elevation models. So in these digital elevation models, actually scientists are creating the elevation models, and they are simulating these models wherein it's possible to, because there was one question in the chat box regarding what will affect the mud in the river basin. So such kind of things, even the changing the conditions like more number of buildings in the terrain of the river. So those things can be addressed by having the digital elevation models. So these kind of models can be created by using the satellite images. And I know that the computational cost is a major issue in this particular domain. And he did talk about the hydraulic models, which is very popular in this prediction kind of river flood prediction kind of things. For computer scientists, the main thing is that the computational cost associated with all these modelings. One thing is we should have data. Other thing is we should have the computational, we should address the computational cost. And nowadays, even the Government of India with CDAC, they have created tensor processing units. So these tensor processing units, they are really helping the hydraulic modeling. And by dividing and conquer approach, one can have the right kind of data-driven discretization, and the two-dimensional hydraulic models can be simulated very, very successfully. And there are many success stories coming up even in India in this particular direction. Because long back, I was associated with a project called as Indo-EX project, the Indian Ocean Expedition, wherein we studied all these things. Of course, Professor Merwade is working on state-of-art kind of things, wherein even the soil moisture, the solar radiations, and all other parameters are taken into account. So overall, a very good talk, and we should thank our Honorable Vice Chancellor for giving us inspiration, and also Professor Merwade for giving us inspiration to have the Center of Sustainability Studies and the climate change in place. And it will really help to address the regional problems like flood in Kolhapur region. Of course, I can see in the audience also many policymakers like Mr. Vadnere is there, scientists like Mr. Purandare is there, our own Professor Raut is there, and of course other eminent persons in the from the DOT also. I can see Mr. Srikant Bosle, Auti, Mr. Auti, and other people who can help in forming the interdisciplinary group, and they can help Dr. Panhalkar, who is keen in doing research in this particular domain. I also like the question which is asked by Dr. Somnath Pawar, who is a statistician, and he is working actively in this particular area. So with that, I won't take much time, because such an excellent talk, and I could summarize from the computational sciences point of view, but really it's an interdisciplinary area. So thank you, Dr. Panhalkar, for giving me this opportunity to summarize this talk. And thank you, Professor Merwade. A lot of things we can do to get together. Even you talked about the machine learning and artificial intelligence. So we can work together in this particular area. and Shivaji University fraternity will be always open for working with you. So with that, I conclude my speech. Thank you very much for giving me this opportunity.
Thank you, sir.
Hello.
Yes, sir. Vadner, sir, would you like to say
Hi.
something?
Hello. Yeah. I was on the way, so I couldn't see the entire thing. But then it was really an excellent delivery by Dr. Merwade, especially the various dimensions, dimensional analysis, the weightings, the way of weightings, and the urban flooding is a really issue. That's what I feel. In fact, the urban flooding is a very complicated issue. As we know, for Kolhapur and Sangli, we worked out for the rivers, and then we adopt this different kind of modeling. It's relatively simpler. But for the urban flooding, the real problem is, how to forecast. That is really the issue. I think Dr. Merwade also stated that even for the normal people, it is very difficult to inform them at what level the floods are going to come at what time of interval. And then that is only possible with the inundation maps. We have prepared inundation maps for Kolhapur and Sangli. Just anxiety, whether the Dr. Merwade sahab, have you really prepared some kind of urban flooding program somewhere in the U.S.?
So I'm not sure what you mean by urban flooding program. So we have a lot of models for many urban cities. So even those models, they do not incorporate some of the information that I mentioned. So what we try to do is we try to show them how they can improve their models. So that's, as a researcher, that's our job, to tell them how they can improve what they are doing. So we, as a university or as my research group, we are not involved in giving flood information to any city or a municipality. So it's their job. So our goal is to inform them our findings.
Yeah. It was. I do appreciate that one.
Yeah.
Because we were worried about the Kolhapur, Sangli, Pandharpur, Pune, and so many such cities in Maharashtra. And the real problem is to let the people know beforehand what level the floods will reach. It's a very complex problem, as we rightly said, even for the modeling, because there are a lot of offshoots, there are a lot of incoming of flood, a lot of outflows. So all the buildings, and then number of, I would say, bridges, dams, and then the things are not that simple.
Yeah.
But then still the problem persists, how to cope up this kind of, because what is the maximum disaster or the damage is done is to the urban, compared to the other areas, So I think awareness is more important, of course. Non-structural measures are more important than the structural measures.
Yes.
Is what we anticipate.
Yeah.
Anyway, I'm sorry that I couldn't join this because I was on the way traveling from Nasik to Pune. Yeah. Thank you. Okay, sir. That's all.
Okay. Thank you for your comments.
Yeah.
So I actually have to go. So thank you, everyone. I hope it was useful. And if you want to get in touch with me, you have my contact information here. So thank you.
It was really useful. It was really useful.
Yeah,
Thank you so much.
Thank you very much, sir.